Because I had a,
I almost
had a,
graduated.
what's it called?
God, I think I failed this.
The word.
I think I got like 7.
See, they got percentage.
I guess what's
They got like, they got beautiful, they even try to house. I don't think we how all I think I'm part.
Page 17.
By that, by sale. Yeah. Big market sale today, everything, out, $200.
Sorry, what page?
Page 17. So this is a problem that you guys, so I think some of you guys have questions about. So I want to work through it with you. This is going through first derivative test, find critical points, and then identify max and mins. So I think the messy part about this is having to do common denominators after you get to f prime. So let's do that. Derivative. All right, let me clean this up so that we can have a more clear picture without the negative exponents. Okay, are we okay so far? All right, now common denominators. Okay, what's a common denominator that's large enough for both of them to multiply into? Okay, between these two, which one is larger? 2/3. Yeah, this is good enough to be the common denominator because we can find something to multiply this to get to that. So our common denominator is going to be 3x to the 2/3. Okay. Now we got to worry about balancing each of the numerators. So between the old new denominator and the new denominator, what will it take for me to multiply with something to get from here to here? X to the what? To the 1/3. And the reason that this works is because remember, if you're multiplying variables, you're adding exponents. So 1/3 plus 1/3 is 2/3. So this works. So that allows my new balanced numerator to be 2x to the 1/3. Any adjustments needed here? No, so I keep the 1, right? Right, so now we can separately look for critical points. So the numerator will set equal to 0, denominator will set equal to 0, and then we'll look for critical points. There. So this one, 2x to the 1/3 equals -1. X to the 1/3 equals -1/2. What can I do to get rid of 1/3? Well, it's already cube root already, so cube it, yeah, good. So we're going to raise it to the 3rd power to get that 1/3 to go away, and we're left with -1/8. This one, if I divide by 3 and raise it to 3/2, x equals 0. Okay, so now we have 2 critical points. Place them onto your f prime sign line, find values in each subinterval, and then now you just read your signs for your max and mins.
Yeah, I forgot. How do we find the relative minimum or the?
Oh, gotcha. So the way you find relative minimum is this is an order pair. So where do you think we need to plug that -1/8 to get that y value?
Oh, cool. Okay.
Into the original function.
Oh, okay.
Right. So the original always gives you location. Yeah. Okay, so today we're going to be talking about the test for concavity, which is essentially the sign line for the second derivative function. But if we're moving to the second derivative function, we're no longer talking about slope, we're talking about curvature or concavity. And then we'll also talk about something called the second derivative test, which also finds max and min. So that's our goal for today, to be able to get through those two topics. And then once we get through with these two, then we've covered all the content for the first half of the unit, and we can think about quiz review or start going through quiz review tomorrow. Again, your quiz will be next Thursday, so we'll have tomorrow, Monday, to review, and even parts of Tuesday. Tuesday, I'm going to cover the content for Thursday, for next Thursday, and then we use the second half of class to review. Wednesday's PSAT day, so that's another day for you to review. And then Thursday morning, I'll have a morning help session before the quiz. So turn to page 19. Yeah, that's about it, yeah. So second derivative test, or sorry, concavity. So the question here is, are both these functions increasing? Yes, they're both positive slopes, but you can obviously tell that even though they're both positive slopes, their graph is a little bit different. Okay? So it's true that both these functions are increasing, but their slope is changing in different rates, right? So here, my slope is becoming steeper, right? So so maybe the slope of 2, then 2.5, then 3, then 4, then 5, then 6. So the pattern of my slope is changing by increasing, right? Becoming more positive, becoming steeper. Here, these are all positive slopes, but what's happening to the slope as we move from left to right? Decreasing, right? Slope of 4, maybe, then 3, then 2, then 1, then 1/2. So the rates of change of their slopes are different. So that means we basically have these two categories of curvatures. One is called concave up. And this is where the slope from left to right is becoming more positive. Or moving in a positive direction. It doesn't mean that the slope is always positive. So if you look here, right, these are all negative slopes, negative slope, but then it becomes positive slopes. But the pattern is consistent. So maybe this is a very steep slope of like -3, right? Then imagine -2, then -1, and then eventually slope 0. Then eventually 1, 2, 3, 4. But if you look at all these numbers, they're all increasing, moving towards a positive number. So that slope pattern moving in the same direction is going to allow the graph to look like this. It'll look like a parabola opening up, and we call that concave up. Again, these are just ballpark values. These are not exact. I just want to show you, you know, if you look at these numbers there, all these slope values are moving consistently in the same direction. Meanwhile, if I have a graph that's concave down, visually it's going to look like a parabola opening down. This is where the slope is becoming more negative. Or the slope is moving in a negative direction. It doesn't mean that it's always negative, but if we look from left to right, all these slope values are going to be moving in the negative direction. So for instance, let's say this is a slope of +4, then 3, then 2, then 1, then slope 0. then -1, -2, -3. And you can see that all these numbers from left to right are headed towards the negative direction. They're all moving in the same direction there. And if that happens, then your graph is going to resemble like a curving downward look. Or it'll represent portions of a parabola that's opening down. Okay, we also have something called a point of inflection, which I abbreviated as POI. So point of inflection is going to be where your concavity is going to change from one curvature to the other. So here, the graph is concave down, and then at some point, it's going to switch over to turning into concave up, and that point of change between the curvature is called point of inflection. You can go from concave down to concave up, but it also works. There's also a point of inflection if we're going from concave up to concave down. So it's that point, that interchange between the two curvatures when the curvature changes. So here it's going to be, let's say this is -3, -2, -1, 0, 1, 2, 3, then 3, 2, 1. So it's that point where the direction of the slope is going to change to go in the opposite direction. So initially it's moving towards the positive direction, and then at some point it's going to switch over to moving towards negative value, and that we call as a point of inflection. All right, so there's all these steps for test for concavity, but I think it's just easiest if we just go through the example, and let me just walk you through the steps. Okay, but essentially, we're doing the same thing as first derivative test. We're just doing everything at the second derivative level. So we're going to find f double prime, set f double prime equal to 0, create the sign line, and the process will feel very similar. But what we find is going to be a little bit different. So find points of inflection, but I also want us to find intervals of concave up and concave down. So we have to takes a little bit longer to get down to the second derivative because we have to get to first derivative before we can move on to second derivative. So let's find f prime first. All we need is power rule. Okay, so this is, we have to keep going, right? So we have f prime, but let's keep going to f double prime. So now set equal to 0. And then you're going to factor and look for your critical points. Okay, so I'm going to set 10x equal to 0. I'll set the -4x squared plus 1 equal to 0.
Why'd you take the negative sign out?
If you can, I just decided not to take the negative out. But if you took the negative out, it's fine. If you took the negative out, it would just be 4x squared minus 1. Yeah. Take the square root. What's going to happen? Plus or minus what? 1/2. Yeah. All right. How many critical points do we have? 3. Okay. So they're going to all go onto the second derivative sign line. So even though the process is going to feel the same, we're at the second derivative level, which means that our interval is not telling us about slope, it's telling us about the concavity or the curvature of the graph. But our process is going to feel very similar. We're going to choose test points. Because we're having to choose a value between 0 and -1/2, I'm choosing -1/4, -0.25 or 0.25. And I'm just going to put it into my derivative function. Sorry, second derivative function. So if I insert -1, 10 times -1 is negative. -4 plus 1 is also negative. So two negatives makes positive. So put a plus sign. But then to help us visualize what this is telling us, it's not positive or negative slope, it's concave up. So this part of the graph, visually, the original function is going to have parts of the graph that will resemble this curvature. If I plug -1/4 in, positive 10 times -1/4, this will give me a positive as well. So I have positive, negative, positive, one negative will give me negative. So I'm going to use a symbol here to indicate what this graph will look like. This portion is going to visually look like parts of a parabola opening down. Plug 1/4 in, positive, positive, positive. Plug 1 in, positive times negative, which is negative. So we have two intervals of concave up, two intervals of concave down. And then what do you think we could call these points? These are good points of inflection because there's a change in sign. It doesn't matter what direction it changes signs in. As long as there's a change in sign, we know that there's a point of inflection. So we don't have a different name for points of inflection that go from concave up to concave down versus concave down to concave up. We just call that a point of inflection. Yes.
Can you explain our testing on the -1/4?
Sure. So the -1/4, if I plug in, well, obviously 10 times -1/4, that's negative. But if I plug in a -1/4 in for x, that gives me a positive 1/16. 1/16 times -4 is -1/4. -4/1/4 plus 1 is still going to be positive. Okay, let's practice writing out the our intervals and because statements because we have different because statements for second derivative function. So we're going to say our function is concave up. I have two intervals, and again, I'm going to cross off the test points. They're not going to be part of my statement. Our reasoning is because f double prime is greater than 0. Our function is concave down. So I have two intervals here, -1/2 to 0, union our reasoning is because f double prime is greater than 0, sorry, less than 0. And finally, point of inflection. If we were to find the order pairs, where would you plug these into? The original. But right now, I'm just going to just indicate the x values. So -1/2, 0, 1/2. And our reasoning is because f double prime changes signs. You don't have to specify the order of direction change. You know how relative max, relative min, we have to specify plus to minus or minus to plus. Here, you can if you wanted to, but you don't have to. You can just say because f double prime changes signs, that will be sufficient. Again, make sure that you're naming the function that you're dealing with. And the one that students tend to leave out in terms of because statements is point of inflection, so just be aware of that. That there's also everything that you find, there's a because statements if you're pulling it from your sign line. Okay, any questions with this process? So it should feel pretty familiar because, virtually the same steps as first derivative test. We're just doing it at the second derivative level. And then as you fill out your plus and minus, just have to remember it's no longer up arrow and down arrow. Positive is going to be concave up, negative is going to be concave down. Okay, and then practice with your because statements. But feels familiar because same process as first derivative test. All right, so this is called the test for concavity. There is something else called the second derivative test. And let's talk about that on the next page. This one can trip some students up. So I want to kind of go over this with you. So page 20. So the second derivative test is a test for relative max and min. It is not a test for point of inflection. It feels like it should be, like what we just did. A lot of students would feel like, oh, that should be called the second derivative test since we're doing using second derivative function. But what we just did is it's called test for concavity. And this is called the second derivative test. It does achieves the same result as the first derivative test. It finds relative max and relative min, just like your first derivative test. And so, some students would ask, wait, why do we need this test if we already have the first derivative test to do basically the same thing? So this is something that is in the curriculum. And also sometimes a problem could be asked on the AP exam where you're forced into this test and you just don't have enough data to do the first derivative test. Oh, just pick up that. Yeah, that will be the classroom set. So this is what I want to show you here. I want to sketch a graph here. And I want to highlight a point here. Now this, you can tell is a what? A relative what? Relative minimum. Okay. So let's say this point ends up being at 1. So that means when everything is said and done, f prime of 1 is going to be 0. But f double prime of 1 is going to have to be a positive value, like let's say 5, which is greater than 0. So the idea is that if we can confirm that a point has a slope 0 and something that returns us that tells us something that tells us that the graph is concave up, then using these two different behaviors on the same point, we can conclude that there must be a relative minimum at x equals 1. All right. And we're just basically pairing, combining information or comparing information between two different behaviors to confirm that, okay, if the slope is 0 and is part of a concave up graph, I must be staring at a relative minimum. Meanwhile, if I have a graph that looks like this, here my f prime of 1 is still going to be 0 because it's going to be a slope 0. But now f double prime of 1 is going to return me like a negative number. Okay. Again, the number doesn't really matter. These numbers are just different ways of representing curvature. These are kind of abstract in a way. The important thing is just understand, okay, positive means concave up, negative means concave down. So if I get a negative value from second derivative and a slope 0 from first derivative, I must be staring at a relative maximum. Okay, so let me show what this process looks like from beginning to end. What we're going to do is we're going to find f prime. We're going to find our critical points. But rather than creating a sign line for the critical points, we're going to take them and plug them into the second derivative function and ask if it's giving us positive or negative value. And then from there, we can determine if we have a relative max from relative min. So let's find f prime. Your initial step will feel like what you would do for your first derivative test. You want to find critical points from f prime. Okay, so let's go through power rule. What do we get? What's f prime? X cubed becomes minus minus 3. Okay, so we'll set equal to 0. Go through factoring. Solve for x. Okay, these are our critical points. Any questions here? Now, normally we would do this, right? Normally you would create a f prime sign line, and then you would plug negative 1/3 and 3, and then you'll test look at your arrows, and your arrows will tell you whether we have relative max, relative min. But this is not the path we're going to go down. Okay, this would be the first derivative test. We're going to go through a different process to determine if these are max and mins. Okay, and that process is going to have to require us to build the f double prime function. Okay, what's f double prime going to be? Let's pick up where we left off here.
6x minus 8.
6x minus 8. Okay. Now, once you have the second derivative function, we're not going to set this equal to 0, because if we did, then we would be going down the concavity test, and that's finding critical points for f double prime. So we're not going to set this equal to 0. Rather, we're going to take these points and insert it into the second derivative function. Okay. So we're going to find f double prime of negative 1/3 and f double prime of 3, and see if our result can help us decide what's happening at that point. So let's test negative 1/3 first. Okay, what do we get? -10. Again, we just have to keep reminding ourselves that the number is not going to be important, because sometimes we look at this number and it kind of throws us off. We feel like it needs to be something that is visual. This is an abstract number. This indicates, the important thing is that this is what? Negative. And if it's negative, let's say this is what? Concave what? Down, okay? And then visualize it. Concave down looks like this. Good. The only place where there's a slope 0 on a concave down is a max. So we can conclude that there must be a relative max at x equals negative 1/3. Don't bring in the -10 in any part of your discussion. Okay, this number is not important. If I want to find the ordered pair, I'll have to plug that negative 1/3 back into the original function. But right now we can just say there's a relative max at negative 1/3. No, because statement. Your work will be your justification. Okay, let's test 3. So we're going to plug 3 into the second derivative function. What do we get here? 10. Again, this number is not important. It's the fact that it's what? Positive. So positive second derivative means what? Concave up. This is what concave up looks like. The only place that you see a slope 0 is this point, which must mean we're staring at a what? Relative min. So we can say relative min at x equals 3. So understanding the process is important. Another thing is these numbers really give students trouble, because sometimes they would say, oh, there's relative max at -10, or relative min at 10. These numbers are not going to be important. It's the fact that it's positive or negative. Now, why do you think students have trouble with this? Why do you think students see this number and they want to say relative min, and when they see this number, they want to say relative max? Because a lot of students, the most common mistake is students want to flip these two around. What's causing us to maybe think that this should be a relative min and this is a relative max? Right, we associate negative with small and positive with high, and so we think of these as physical points on the graph. But again, this is a curvature value. This is an abstract value. We have to consider, okay, this means concave down. This concave down looks like this. I must be staring at a relative max. So just be aware that that this is going to throw you off potentially, right? So if you're not careful, where you're going to want to interpret this as a low number, therefore relative min. You're going to want to interpret this as high number, therefore relative max. But they're talking about curvature, and so concave up and concave down is how we want to determine max and mins. I just want to show you, let me see, is there a room on? Yeah, I just want to show you what a problem could look like on the AP exam in terms of, how they may force you into the second derivative test, and without being able to use the first derivative test. So let me just show an example here. Let's say the function is differentiable. So let's just establish that the graph is going to be a smooth curve. And then you're given three sets of information about the same point. You're told that f of 2 is equal to 5. You're told that f prime of 2 is equal to 0. And then you're told that f double prime of 2 is equal to -121. And we're going to try to make a conclusion as to what can we conclude about this point. So this is just a single point, right? That's just an order pair that physically lives on the graph. This means that my graph has a what? What does this mean? At 2, there's a what? Good, slope is 0. And then at 2, there's a what? Because this is concave down. So we have to, these are all giving us different sets of information about the same point. The order pair is giving us the location, the derivative is giving us the slope, and the concavity is telling us the curvature that is part of. So we can put it all together that this is telling us the graph is looking like this, and we must be staring at a relative max at x equals 2. So we're going to practice a bit more, but I just want to show that, a lot of students see that -121 and they want to think something that is low and they want to say min, but we have to connect this number with just negative, and negative means concave down, and concave down looks like this. I must be looking at relative max. So. Right, so we've covered all the new content. Let's see if we can do some practice across different types. Let's do 41, page 21. So here are the instructions. We're going to find the local relative extrema of f. So we're going to go through the first derivative test. We're going to go through test for concavity, and then find points of inflection. So we're going to basically do the sign lines for f prime, and do the sign lines for f double prime, and list out all of our characteristics. Okay. So let's find f prime, page 21, number 41. Set equal to 0, factor your GCF out. Oh, sorry about this one. This one is difference of cubes. I'm not going to ask you to have to factor this, but let me just write it out for you. Okay, there's nothing that's going to come out of this. It's just going to be one critical point at x equals 1. Again, we're not going to have to do this. So just for now, just go through this process with me. And the only critical point is at x equals 1. There's nothing that's going to come out of this trinomial. This is going to give us an imaginary number. So just that one. Okay. Find test points on either side. Plug into your f prime. I plug in 0, I get negative. If I plug 2, I get positive. So we can make a statement about relative minimum. We can make a statement about decreasing. We can make a statement about increasing, but no relative max. It says determine just local extrema, but let's just practice writing out all of our characteristics as well as because statements just for practice purposes. So we can say and I want to find the order pair here. So I'm going to plug 1 into the original function. Okay, so we've gathered everything that we can from the sign line for f prime. Now let's move on to f double prime. So we'll pick up where we left off. Power rule again from f prime to f double prime. The constant goes away. What's the only critical point here? Divide by 12, square root, yep, x equals 0. All right, choose test points. Make sure you plug this into the second derivative function. Negative gives me a positive. Positive 1, also positive. Okay, do we have points of inflection here? No, there has to be a change in what? Signs, yeah, there's no change in signs, so no points of inflection. But let's still write out our interval of concave up in 2 separate intervals. I just find it safer to just do it that way. Sometimes you can combine it, but if you always keep it separated, you're never gonna have to worry about, losing points because it could have been combined.
Do we just state that no point of inflection, like?
Yeah, in this case, it says find any points of inflection. So for part C, you just say none. Yeah. But on the quiz, I'm going to ask you for all the characters, or I'm going to ask you for specific characteristics, and you're just going to just fill that space in.
So it's like no POY because.
Because f double prime doesn't change signs, right? Yeah. Yeah, we can. Yeah, let's do that. Let's do a second derivative test practice. So let's go to page 23. And we're just going to do the second derivative test on page 23. So remember, second derivative test achieves the same purpose as first derivative test. It finds max and mins, but the process initially looks like first derivative test, but instead of creating a sign line, we're going to put the critical points from f prime into second derivative. So let's go through the steps. So I boxed off my candidates, and I'm not going to create a sign line. I'm going to find the second derivative function and put those candidates into my second derivative function.
Well, you have some of the questions on the quiz where it's just like you just go straight to the second derivative test.
Right, I'll specify use second derivative test to find this, use first derivative test to find this.
Okay.
Yeah, so I'll specify exactly which method I want you to use.
Think.
Yeah, f double prime. Now we're inserting these x values into the second derivative function, right? Again, we really have to not pay attention to these numbers. Just consider it positive and negative, but that's all we care about. So these numbers are not going to play a role except to tell us whether it's positive or negative. All right, so at 0, my concavity is value is negative 16. That's less than 0, so that tells me what? Concave down. If it's concave down, I must be staring at a relative max. Good. We don't know the y value, so just say relative max at x equals 0. Thirty-two is not that important. It's the fact that it's what? Positive. Positive second derivative means concave up. Look at what concave up looks like. I must be staring at a relative. And don't bring in the 32, negative 16, or 16 in any other parts. Some students want to say that's the y value. This is not a y value. This is just some abstract curvature information.
With the values, Scott, because it's double prime, does that have anything to do with the slope? Like the rate of change?
This tells us that the slope is changing at this rate. So it's changing at a steep rate, but visually it's kind of hard for us to see it. So we don't worry about it. We just know that, okay, it's concave up, and that's all you need to worry about. All right, so here, same thing, right? Concave up. So therefore, there's a relative what? Yeah. Okay, your homework, just a few problems here. Page 25, just 15 and 17, just 2 problems. Homework. It's just finding points of inflection and writing, going through the concavity test for concavity.
James. Can I just show you this lessons guy?
And I don't want that. Sorry. Everything.
Oh, yeah, mystery.
Like,
I finished
it's
page
not
seven.
everything.
Okay.
No, I'm not even like kidding you.
Is it similar to the process?
There's a couple questions from it, but like there's so much other random stuff.
Yeah, like, do you remember the raccoon one?
Yeah, right.
The raccoon. It's second down. That one, there's the orchid mantis one.
Okay.
I feel like those are the
Exactly. Yeah, the orchid mantis one though, that's the one where it's like, the orchid, yes.
Dude, I just didn't know.
The orchid mantis one is like, the orchid mantis